All right, so this is section 10.4, day 1, video 2. In the first one, we kind of learned how to find the slope at any given point, find dy over dx. It was that very long formula, which we will still be using. Um, and we also talked about how to find the tangent line at a pole. Um, so in this one, in this example, we're going to identify the equation of the tangent line to the polar curve that's given at theta equals 3 pi over 4, and then write the equation in rectangular form. So it's asking us to find the equation of a tangent line, okay, not the equation of the tangent at the poles, the equation of the tangent line. So basically at one specific angle, we're going to have an equation of a tangent line, you know, like for lack of just any, specific example, like y minus 2 equals 7 times x plus 1 or something like that. That's your point slope form, which we will utilize in this. So in order to do that, we basically need an x value, we need a y value, and we need the slope. So we can find all of those things from the given information. To find dy over dx. Okay, we need to utilize our formula. It's that long formula. So we're going to need a few things. We're going to need f of theta, which we are given. That's r. We are going to need f prime of theta, which is going to be the derivative of r, which is, let's see, what's that going to be? Cosine theta. Derivative of negative cosine is positive sine of 2 theta. Times the 2 from the chain rule. So there's f prime of theta. And then, of course, we're going to need the slope. But we're going to need f of theta and f prime of theta at 3 pi over 4. You can find it algebraically first if you want to, or we can plug in the values and let's see what we get. So let's do f of 3 pi over 4, which might make it a little easier later. Let's see, if we plug in 3 pi over 4, we're going to get sine of 3 pi over 4, which is root 2 over 2, minus, let's see, cosine, that's going to be 2 times 3 pi over 4, so that's going to be 3 pi halves. Cosine of 3 pi over 2 is 0. So really, that's just going to be root 2 over 2. Okay, that's kind of nice. We're going to need f prime at 3 pi over 4. Which is the one that we just found. So that's cosine of 3 pi over 4. That's negative root 2 over 2. And then that's going to be 2 times the sine of 3 pi halves. Sine of 3 pi halves is negative 1. So times the 2 out in front gives us negative 2. So there's our f prime of 3 pi over 4. We're going to need to utilize all of that information in our derivative. So let's find our derivative. We know that it's f prime first, f prime of theta times sine of theta plus f of theta cosine of theta all over f prime of theta cosine of theta minus f of theta sine of theta. All right, and the nice thing is, like I said, we found the values at 3 pi over 4. So now we can do dy over dx when theta equals 3 pi over 4. So f prime at 3 pi over 4 we just found to be negative root 2 over 2 minus 2 times sine of 3 pi over 4, that is root 2 over 2, plus f of theta we found to be root 2 over 2 times cosine of 3 pi over 4, which is negative root 2 over 2. All right, the denominator. The nice thing about the denominator, it utilizes f prime of theta and f of theta, just like we did, so we can kind of fill those in. Okay, that part doesn't change. This part doesn't change. Cosine of theta we just found on the top, which was the negative root 2 over 2. minus, and then the sine of theta, which is positive root 2 over 2, goes there. So not too difficult to fill all that stuff in. Now we get to do all the simplifying. Yes, that is the derivative. Yes, technically that is mathematically correct. It is not very usable at this point, so let's simplify it the best that we can. If we distribute the root 2 over 2's or the negative root 2 over 2's into the parentheses, we should get, let's see, distributing the first one here, that's going to give me negative 2 over 4, so negative 1/2. And then 2 times root 2 over 2 is going to give me root 2. Okay, so that's the first one on the top there. Plus, actually that should be minus now because I'm multiplying a positive times a negative. Again, root 2 times root 2 is 2 over 4, so that's 1/2. So there's the numerator so far. Denominator should be similar, except that the first one on the bottom here, when we distribute that negative root 2 over 2 through, is going to give me a positive 1/2. And then a positive root 2, so plus root 2. And then it'll be minus, still be a minus 1/2 in the denominator. So let's simplify a little bit further. On the top, we've got a negative 1/2 and a negative 1/2 added together is going to give us a negative 1. And I still have that minus root 2. In the denominator, it's a little bit nicer. I got a positive 1/2 minus 1/2. Those are gone, which just leaves it over root 2. That's probably as good as we want to have to go here because you're not, I mean, you can rationalize, which is perfectly fine, just not necessary. If we were to rationalize just to do it, you would multiply the top and the bottom of this thing by root 2 over root 2 to rationalize it. So then we would get negative root 2 minus 2 over 2. Again, either one of the two forms that are right here are perfectly fine. The rationalization part is not necessary. I don't think it's going to help us at all. But either one is perfectly fine. Those are your slope. That's your derivative. That's the hardest part of this whole thing. We still do need, however, x and y. So this is where the converting from polar to rectangular comes in handy. Remember that x is r cosine theta. We've already figured out r to be square root of 2 over 2 times the cosine of theta, cosine of 3 pi over 4, once again, was negative root 2 over 2. So that's going to give us negative 1/2. And then y is r sine theta, so again, root 2 over 2, times the sine of theta, which is also root 2 over 2. So that's positive 1/2. So now we have everything we need to write the equation of the tangent line. It's not going to look pretty, but this is the equation of the tangent line. It is y minus 1/2 equals the slope. I'll go with the rationalized version. Doesn't really matter. Times x minus, or in this case, plus 1/2 because it's minus 1/2. And there's the equation of the tangent line at the specific point or at the specific angle when theta equals 3 pi over 4. All right, again, these are long examples, so we may end up having to do a fourth video, we'll see. Now let's talk about the idea of area enclosed by a polar curve. It's not much different than area between curves, except how we measure everything is going to be now based upon polar coordinates. So here's the general idea. The formulas down here are actually pretty easy overall. The area formula is given as, this is probably the easiest one to use, the integral from alpha to beta, which are just two angles, of 1/2 of the original function of theta squared d theta, or 1/2 r squared. The concept is, if I have some kind of a polar curve, okay, whatever this polar curve looks like, I don't really know, could do a whole bunch of different things. You could try to take the area of that using x's and y's. It'd be kind of difficult because, as you can see, it's not a function in x and y, so you'd have to split it up and do a whole bunch of different things there. It's much easier in polar. So let's say that alpha and beta intersect the curve at those specific places right there. So maybe the ray that comes out of here hits there, and we'll call that alpha. The ray that comes out of the pole hits there, we'll call that beta. So we're trying to find the area. Let's see how well I can do this. Let's go with the highlighter. We're trying to find this area in here. I was never very good at coloring, staying between the lines, but that's not too bad. That's the area that we're trying to find. So the idea is, what we need to do is we need to find the area between that curve and the pole. So we are trying to basically break this thing into nice little small segments that would look like that. And then you'd find each one of those shaded, like everything here that's going to be in that blue area. And then you would add a whole bunch of infinitely small ones of those. Well, what these are not going to be rectangles like we're used to doing. So we're not adding up a bunch of base times heights. What you're actually adding up here are circular wedges. Okay, this basically, when you make these incredibly small, would basically be like a circular wedge because it comes from or emanates from the center and then goes out and creates a wedge at the end of this. So it's a bunch of circular, or I guess wedges, arcs, whatever you want to say. That's the idea of what we're doing here. And then we're breaking that up and integrating from alpha to beta. From, your A to B, in this case, alpha and beta. So hopefully that makes sense as to what you're doing. And the hardest part here is sometimes going to be figuring out what are my alpha, what are my beta. But again, a lot of that just comes down to your trig knowledge, how much you understand how the trig stuff works. When we get to the examples, hopefully we'll be able to show this a little bit better. You can read all the stuff that's here with all the guidelines and things like that, but hopefully that illustration does it, and the formula itself is not very difficult to utilize. So go ahead and read the guidelines and everything like that if you need to. But let's go through example number 5. Example number 5 says, find the area of the region in the first quadrant that is within the cardioid 1 minus cosine of theta. Now again, you don't have to necessarily know the shape of this, but you can plug that into your calculator to see what it looks like. Ultimately, whatever this thing is doing in the first quadrant, however, that the fact that it says first quadrant is helping us because it gives us our bounds. The only thing you have to know, and this does come up in the future, is do you have any tangents at the pole in the first quadrant that we'd have to deal with? If you do have tangents at the pole, that's going to make a difference as to how we do this problem. We do not in this case. I probably should go ahead and pull this up so we can take a look at it though. All right, so I brought the calculator up here. Let's see what this particular function looks like. Let's just type right over that 1 minus cosine of theta and see what this thing looks like. Ooh, okay, I have to zoom out. It's actually a little bit too. There we go. Okay, that doesn't actually do it justice. Let's try a different zoom. Let's try zoom trig. See what that does. Huh. Okay. For some reason, the left-hand side looks more vertical than it's actually supposed to be a little smoother than that, but I'll sketch it on the page here so we can take a look at it. So really what it's just supposed to look like is this. I will not do it justice, I am sure. Kind of looks like a sideways heart. But what it says we're supposed to be doing is we're supposed to be looking for the area that lies in the first quadrant. So all that is that blue shaded region right there. That's what we're looking for, which means that we basically need to go from 0 up to pi halves in order to what's called sweep the region. We're going to sweep the region that is enclosed in that little part of the cardioid there. If you kind of think of putting your pen or putting a pencil on the x-axis and figuring out what type of rotation it's going to take to cover the entire region that they're talking about, that in this case is going to be from 0 to pi halves. So the formula itself is easy. A equals the integral from alpha to beta, 0 to pi halves, of 1/2 of my r part squared with respect to theta. Again, formula is easy. Now we get to do all the algebra, all the antiderivatives, using trig, identities, all that kind of good stuff, because this is where it's all going to come into play. And this is why these problems can take a little bit of time. You have to be able to do this stuff. And some of these will be necessary to be done by hand. So make sure you're good with this. First of all, there's a 1/2 that is being multiplied. It's a constant. I can pull it out to the front. And in order to do the 1 minus cosine that quantity squared, there's no way to do a u substitution here because there's nothing to get rid of on the outside. So we're basically going to have to expand this. We're going to have to distribute or FOIL it out, however you want to think about it. When we do that, you're going to get 1 minus 2 cosine of theta plus cosine squared of theta. At this point, I assume that if we're in Calc 2 that we can FOIL that stuff and not have to worry about the algebra too much there. All right, are we completely ready to take antiderivatives? Not quite. Close, but not quite. We can take an antiderivative of 1 with respect to theta. That's easy. We can take an antiderivative of -2 cosine theta. That's easy. Cosine squared, however, is not an easy one to do. Okay, because remember, that is a product of cosine times cosine. Could you do an integration by parts? Absolutely. Probably not the easiest way to do it. So let's use an identity, and I'm going to give you 2 of them that are very important for this unit. Cosine squared of theta is the same thing as 1/2 of 1 plus cosine of 2 theta. This is called a power reduction formula. Fortunately, sine squared of theta is very similar, and if you know one, you're going to know the other one. Just don't get them backwards. Sine squared of theta is 1/2 1 minus cosine of 2 theta. And these were also introduced back when we did higher order trig integrals, but I'm just reintroducing them here because we will need them. And we need it right here. So we're going to have 1/2 the integral from 0 to pi halves of 1 minus 2 cosine of theta. Now we're going to use our identity. Cosine squared is 1/2 of 1 plus cosine of 2 theta. And we'll finish off with d theta. Now we want to simplify because I've got that 1/2 on the outside of the parentheses within the middle part there. So let's distribute the 1/2 through, not the 1/2 from the outside of the integral. We're going to take 1 minus 2 cosine theta. Now we'll distribute this 1/2. So we're going to get 1/2 plus 1/2 cosine of 2 theta d theta. And we've got one more step to simplify before I think we should take antiderivatives. You don't have to, but I always prefer to combine any things that I can. So I'm going to combine the constants. I've got a 1 and I've got a 1/2 here. Let's add those together and we'll get 3/2 minus 2 cosine of theta plus 1/2 cosine of 2 theta d theta. We're still integrating, haven't taken antiderivatives yet, but now I think we're ready to do so. All right, so we've still got a 1/2 out front. Antiderivative of 3/2 will be 3/2 theta. Normally it would be x, but we're using thetas here. Antiderivative of -2 cosine of theta is going to be -2 sine of theta. And then the antiderivative of 1/2 cosine of 2 theta. Now you could use a u substitution here, but there's a trick that I introduced in the prior videos that says if the composite function, or in this case our angle, is linear, 2 theta is linear in nature, then you just have to multiply the front by the by the reciprocal of the slope. So 2 theta, the slope would be 2. Multiply it by the reciprocal, which is 1/2, or you could divide by the slope. Either way. So what we're going to get is we're going to get the antiderivative of the cosine part, which is sine. Okay, the angle doesn't change, but then I have to introduce an extra 1/2 multiplied out in front times the first 1/2, which now gives me 1/4. And then we're going to evaluate that from 0 to pi over 2. All right, so let's plug this stuff in and see what we get. We still get a 1/2 out front. Plugging in pi over 2, that is going to give me 3 pi over 4. Plugging in pi over 2 where the sign is going to give me sine of pi over 2 is 1, so that's going to be -2. And then sine of, that's going to be 2 pi times pi over 2, that's pi. Sine of pi is 0, so that's done. Minus, plugging in 0, this one's really nice. 0 times 3/2 is 0, sine of 0 is 0, sine of 0 is 0, so that is gone. So now all we have to do is distribute our 1/2 through, and we're going to get 3 pi over 8 minus 4. I'm sorry, minus 1. 1/2 times 2 is definitely not 4, it's 1. There is our area of that tiny little sliver of the cardioid up there. 3 pi 8ths minus 1. All right, number 6 here says, find the area within the entire cardioid from example 5. Well, do I need to really redo the entire process? No, because I've already done all the antiderivative and integration stuff that we have to do prior to that. All I need to do is change the bounds. Because now if I want to find the entire area, to sweep this whole thing, I've got to go all the way around to cover everything. So it's going to be from 0 to 2 pi. That would sweep the entire region. So we are going to take the integral, we'll at least set it up. So the area will be the integral from 0 to 2 pi of 1/2, and it was 1 minus cosine of theta squared d theta. Jump all the way down to the part that we've already done. Again, there's no reason to redo all the work. So we'll have 1/2 3/2 theta minus 2 sine theta plus 1/4 sine of 2 theta, evaluated from 0 to 2 pi. Plugging in a 2 pi, oh, this one's going to be really nice. If you plug in 2 pi into the first theta, you're going to get 3/2 times 2 pi, which is going to give you 3 pi. So still got the 1/2 on the outside here. We've got 3 pi. Watch what happens now. Plug in 2 pi into the 2 sine of theta, sine of 2 pi is 0. Plug it into the sine of 2 theta, sine of 4 pi is also 0. That's gone. Plug 0 into all of the rest of the thetas, all of those are 0. So we get 1/2 times 3 pi, or 3 pi halves as our area. That one worked out quite nicely. All right, as I said, these problems take a long time to do. That one took quite a bit of time to get through, so we'll end the video here, and we will come back with a third video, and if necessary, a fourth.